Hello everyone, I am going to present the paper MalEfficient10%, a novel feature reduction approach for Android malware detection. The co-authors of this paper are Hemant Rathore, Ajay Kharat, Aditya Manikavasakam, Sanjay K. Sahai and Mohit Sehwag. I would like to thank EAI Broadnet for accepting our paper and allowing us to present in the conference. So the agenda for the presentation is as follows. I'll be starting off with the introduction, followed by the contributions of the work, the proposed framework, the experimental results, the experimental setup, the results, the result analysis, followed by comparison with related works and the concluding remarks. So, more than half of the world use smartphones for their day-to-day activities. According to the International Data Corporation, Android holds more than 72.2% market share of the global mobile phone OS. It is expected to reach 80% by the end of 2023. Hence, Android is a very lucrative target for malware developers. More than 33 billion malware has been identified in the Android ecosystem as of Jan 2020, according to AV test report. We can see that it has been growing significantly from 2012 onwards. At least 40% of the world's mobile phones are vulnerable to malware attacks. This was given in the McAfee's mobile report. Hence, there's an urgent need for proactive detection of Android malware. Now, conventional malware detection systems such as signature-based and heuristics-based, they are ineffective against unknown malware. Hence, there is a shift towards machine learning-based malware detection systems. Machine learning-based detection systems can be broadly classified into static analysis-based malware detection and dynamic analysis-based malware detection. In static analysis-based malware detection, the inner working of the Android application is going to be examined by dissecting the application without executing it. In dynamic analysis, the application is going to be run in a sandbox, and this process is a resource-intensive and time-consuming process. Hence, in this paper, we are going to be considering static analysis-based malware detection. Analysis involves extracting features from the Android apps. These features are high-dimensional and can lead to high computational cost and large strain and test time, but with little to no improvement in performance. Hence, feature reduction is crucial in static malware detection. To analyze only the most contributing features, we need an efficient and effective Android malware detection system. So the contribution of our work are as follows. We propose a novel feature reduction approach which reduces each feature set to 10% of its original size while maintaining high performance. We built 26 baseline malware detection models without any feature reduction using 724 features, and we achieved an average accuracy of 74.7% and average AUC of 94.49%. With feature reduction, from 724 features to 72 features, the models achieved an average accuracy of 93.12% and an average AUC of 92.97%. So this feature reduction from 724 to 10%, that is 72, it resulted in only a minor reduction of 1.69% in accuracy and 1.60% in AUC respectively, but the average training time was improved drastically by 85.26% and the average testing time was improved by 91.45% for the 26 Android malware detection models. So the proposed framework is as follows. The Android apps are collected from Drebin, AMD dataset and Google Play Store. The Android permissions, intents and opcode feature sets are extracted from each Android application by reverse engineering. We then construct baseline malware detection models using the original permissions, intents and opcode feature sets. Each feature set is then reduced to 10% of its original dimensions using the proposed algorithm. We also combine all the three feature sets to form a merged feature set and then reduce it to 10% of its original size. Finally, the effect of feature reduction on the model performance and time is evaluated. So the proposed feature reduction algorithm is as follows. It has two main functions, independent and merging. So independent takes in each feature set as input and it returns the reduced feature set. It initializes the reduced feature set to null, or the original feature set f is given to a traditional feature selection method using getSelection. It returns a feature importance score for each feature. This is used to sort the features and identify the top 10% most contributing features in F. In merging, the permissions, intents and opcodes are merged to form a single feature set. The top 10% features of the merged feature set is found using the independent function and return. The final list of Android features after feature reduction is given in this slide. So 192 Android permissions were reduced to just 19 permissions, 273 Android intents were reduced to just 27, while 256 Android opcodes were reduced to 25 opcodes. Coming to the experimental setup, we considered two data sets. The first data set used Debian as its malware data set, and the second data set used Android malware data set AMD as its malware data set. The benign applications were downloaded from Google Play Store, and each application was verified using VirusTotal. Coming to the feature extraction, each executable was disassembled using a feature software called as APK tool. We passed the files to obtain 192 permissions, 273 intents and 256 opcodes. Now permissions are useful for malware detection because they control access to data such as system data and user data, and they also control actions such as accessing the internet, recording audios, etc. Android intents allow communication between components. This can result in easy access to highly sensitive services in the Android system. Opcodes are the first byte of an instruction. It indicates actual operation performed by the processor and it can detect attacks at the lowest level of the architecture. Hence we've used these three features. We used 13 different classification algorithms in 4 different categories to demonstrate the generalizability of the proposed approach. We use classical machine learning classifiers such as decision tree, logistic regression and KNN, as well as ensemble techniques such as bagging, boosting and deep neural networks. So the performance metrics used for evaluating our proposed approach are as follows: true positive, true negative, false negative, accuracy, which is the number of correct predictions over the total number of predictions, and area under curve, which denotes the detection performance across varying classification thresholds. Finally, the training time and testing time. Coming to the experimental results. So first we'll be showing the results for the original independent PIO features for Debian and AMD. Next we'll be showing the reduced independent PIO features for Debian and AMD. Finally, we'll compare the results for the merged feature set before and after feature reduction. So for the original permission intent and opcode feature sets of 195 permission, 273 intents and 256 opcodes, we can see that extra trees classifier has achieved the highest accuracy and AUC for permission and intents, and while ADA boost has achieved the lowest accuracy and AUC of 91% for permissions, while K-nearest neighbors has achieved the lowest accuracy and AUC of 67 and 62% for intents. Extreme gradient boosting has achieved the highest accuracy and AUC for opcodes, while backed SPM has achieved the least accuracy and AUC of 80.6 and 81.9 percentage for opcodes. Coming to the AMD dataset, we can see that Random Forest has achieved the best accuracy and AUC for permissions, while Extra Trees has achieved the best accuracy and AUC for intents. Extreme Gradient Boosting has achieved the highest accuracy and AUC of 98.3% for opcodes. ADA Boost has achieved the least accuracy and AUC of 92.9% for permissions, while K-nearest neighbors and logistic regression have achieved the least accuracy and AUC for intents, while logistic regression has achieved the least accuracy and AUC for opcodes. Coming to the reduced permission intent and opcode features, so 192 permissions have been reduced to 19, the 19 most contributing permissions. Similarly for intents and opcodes, light gradient boosting mission, K nearest neighbors, and DNN1L have achieved the highest accuracy and AUC for permissions, while extra trees has again achieved the highest accuracy and AUC for intents, while and for opcodes. Coming to the AMD dataset for the reduced PIO features, we can see that Random Forest has achieved the best accuracy and AUC for both permissions and intents, while Extra Trees classifiers achieved the best accuracy and AUC for opcodes. Adder Boost has achieved the least accuracy and AUC of 89 and 90% for permissions, while Logistic Regression has achieved the least for both intents and opcodes. And we compare the performance between the models trained on the 724 merged features and the models trained on 10% of the merged features, that is 72 features. Considering the Debian dataset, we can see that Random Forest, Extra Trees, and all the boosting algorithms almost have the same accuracy even after reducing to merely 72 features. XGBoost has 98.03% before feature reduction and 97.86% after. Extra Trees classifier has the best AUC of 98.07 before and 97.65 for the after feature reduction. All the classical machine learning, bagging, and boosting algorithms demonstrate almost equal AUCs. Coming to the AMD dataset, decision tree, random forest, extra trees classifier, and all the boosting algorithms have achieved nearly 100% accuracy for both 724 and 72 features. This can be seen in the AUC as well. So decision trees, random forest, extra trees, and all the boosting algorithms have achieved nearly 100% AUC for both before feature reduction and after feature reduction. When we compare the training and testing time, while training the models for the merged features and the reduced features, we can see that for the Debian dataset, the highest reduction can be seen by DNN5 hidden layers with a 93% reduction in training time, while the least training time reduction can be seen by random forest with 41%. Testing, the highest reduction in testing time is close to 100% for the decision tree and logistic regression, while the least reduction is by random forest with only 25% reduction in testing time after feature reduction. For the AMD dataset, the highest training time reduction has been achieved for the K nearest neighbors with 92.18% reduction in training time from the merged features to the reduced features, while the least training time reduction is obtained by logistic regression with 46% reduction in training time. The highest reduction in testing time has been achieved by logistic regression with 95% reduction in testing time before and after feature reduction. The highest reduction in testing time after feature reduction has been noticed in logistic regression with 95% reduction in testing time, while the least reduction in testing time is seen in random forest with 60%. Summarizing the results, we have reduced 195 permissions to 19, 273 intents to 27, and 256 opcodes to 25, with a very minute effect on accuracy and AUC. The three feature sets were merged and then reduced from 724 to 72 features, and this resulted in only an average accuracy reduction of 1.69% and an average AUC reduction of just 1.6%. But the testing time improved drastically by 91.45% on average for both the Debian and AMD dataset, while the training time improved by 85.25% on average after the feature reduction. When comparing with existing literature, our proposed system reduced the merged feature set to 10% of the original, that is 724 to merely 72. We also validated the generalizability of the proposed approach by building machine learning models for 13 different machine learning and deep learning algorithms in 4 different categories. We achieved the highest detection rate of 99.99% for the AMD dataset after feature reduction on the merged feature set. We also published the final list of permissions, intents, and opcodes after the reduction. So most of the previous research in this domain based on a single feature space like permissions and opcodes, but this will result in malware detection models which are more ignorant than models which are trained on a variety of features. Previous research have also focused on improving the detection performance at the cost of efficiency by using large feature sets. This is counterintuitive, as large feature sets can lead to overfitting and the curse of dimensionality, reducing the model's real-world performance. It also increases resource consumption, training time, and evaluation time. Studies that have performed feature reduction have not validated their approach and feature set using a variety of machine learning-based malware detection models. The selected features were also not published for further validation. Thus, Android is heavily used across the world. There is an urgent need for detection of Android malware. Feature reduction is a necessary and crucial step to reduce computational cost and time. Hence, we proposed a strategy to reduce each feature set to 10% of its original. We demonstrated its effectiveness with different experiments. We drastically reduced the average training time by 85.2% and the average testing time by 91.45%. We have obtained an average accuracy of 94.7% before feature reduction and 93.12% after feature reduction, resulting in merely 1.69% accuracy reduction. Similarly, the average AUC of 94.49 was reduced to 92.97 after feature reduction. This resulted in a mere 1.61% AUC reduction. Hence, the proposed approach massively decreased the train and test time while achieving high detection performance, which is comparable to the original high dimensional feature set. Thank you.